So you know that expression, I think, therefore I am. The I think part, that's the premise, the thing that we assume to be true. And the therefore I am, that's the natural conclusion, that's the outcome of the argument. The point of that statement is that if we remove all our beliefs, what is the most basic and fundamental thing that remains? Even if you question and doubt everything, the one thing that we can be certain of is there's something that remains that is doing the doubting and the questioning, the thinking. So an interesting debate in AI right now is, do these AIs, do these neural networks, these machines, do they think? Do they reason? Do they understand? There's no consensus. We have incredibly smart and accomplished AI researchers that think that they do. Andrew Ngo and Jeffrey Hinton are two such examples. And we have incredibly smart and sophisticated AI researchers that think that they don't. Yann LeCun is one example. Well, in the past few weeks, we got two different papers that might shift this debate one way or another. Today, let's look at a paper called Beyond Surface Statistics, Scene Representations in a Latent Diffusion Model. Really fast, let's define what understand means. Stick with me for just 10 seconds. This is important. What does it mean if we ask if a machine understands? Just knowing the answer to a question doesn't mean that something or someone understands. They could be just reciting it from memory or maybe just had a lucky guess. For example, thousands of years ago, some guy said that the Earth is 250,000 stadiums long. They measured everything in stadiums back then. I don't know. We know how long the stadiums were back then. And yeah, he was kind of close to what we know today as the circumference of the Earth. Now, we know what it is because, we can go up there with spaceships and see what it looks like. We can measure distances with satellites. We can pinpoint specific locations and moving objects with the Global Positioning System, GPS. Like, we have that data now. We can see it. We can measure it. You get it. But how can we possibly know if that guy, thousands of years ago, if he actually understood what the Earth was, how big it was, what was its shape? How do we know if he truly understood it or that was maybe a lucky guess? 250,000 stadiums doesn't even sound like a calculated number. That looks like something you might guess. So the point is the actual answer doesn't really matter in terms of determining if something or someone understands. So with our stadium guy, he knew the distance between two places in Egypt, Alexandria and Syene. So when the sun was directly overhead in Syene, at that same time, he measured the shadow that was cast by the column of Alexandria. And having those data points, he figured out the circumference of the Earth. So now if you ask if he really understood what the size and shape of the Earth is, all of a sudden, yeah, it really sounds like he did. It sounds like he knew exactly what it looked like, how big it was, etc. He understood what it was. He was 50 miles off from what we know today, but still, I don't think there's any doubt that he understood how big the Earth was and what shape it took. We know that because he built a model, a math model or a mental model, and he was able to predict or infer something for which he didn't have the data. He had to build a mental model to figure it out. So with that said, in another previous video, we saw a paper where a large language model was fed nothing but moves from a board game called Othello. So this was a GPT-based model, like GPT-4. It was like that structure, GPT. But this is important. It didn't get any word data yet. So it wasn't fed textbooks and words and the internet. No data has been fed into it. It was a blank slate. And then we fed it Othello moves one game at a time. So for example, here's the input of a typical Othello game. So a board is like this. So here's a board, right? So you have A, B, C, D, E, F, G, and then 1, 2, 3, 4, 5, 6, 7, 8. Each square on the board can be represented by, for example, A1 or E4, etc., right? So here's a typical game, F4, F3, D2, F5, G2, F2, G3, you get it. So each of these board positions, they were like words for a large language model. And the entire game was kind of like a sentence. All right, so it was fed in this game and then it started over again and again and again, probably millions of times until this thing got pretty good at being able to predict a legal move that would come next. So this is the thing that a lot of people miss. So this is the input. This is the only input it received. It received no English words or any other language. It wasn't told about the board, the existence of a board. It wasn't told about the existence of tiles. Like basically, if it didn't look like this, just a series of board moves, it didn't know about it. Its entire knowledge base was this, what you see right here. And so in the end, it learned to predict what legal move could come next, which is what we would expect. This is the sort of thing that it's supposed to do. If it's just a fancy statistical calculator that predicts the next move, that's just based on surface level statistics, we expect that it would be able to do that. No surprises there. However, when the researchers started looking inside to figure out how it was predicting these moves, they used something called probes. And a different paper describes exactly what probes are. Basically, it's taking the model and kind of slicing it into two pieces and trying to figure out what happens during different moves. I kind of think of it as if you've ever seen that experiment where during brain surgery, the doctor can prod a portion of somebody's brain and like their finger twitches or whatever. We can kind of see which areas of the brain respond to which functions in the body, just a little bit. So we don't have full visibility into it. We can kind of see what happens where. So when they looked inside this model to see how it was predicting the moves, it appeared that this AI developed a mental model of the board and could also accurately predict the state of the board, meaning it knew which squares were empty and which squares had the white and black pieces on it. Now, again, it had no concept of white and black or tiles or squares. But if we said, okay, let's call one my color and one the opponent's color, it could figure out which one was which. So this is lesswrong.com. So the context is, and this is the paper that they're talking about. So they found that it spontaneously learned to compute the full board state, an emergent world representation. And we can causally intervene on this representation to predictably change model output so it's telling us something real. So in other words, just like our stadium guy thousands of years ago, he looked at a shadow and then figured out how big the planet was. This is doing, I guess, something similar in a sense that it's looking at all these moves and creates this world representation for itself, a world model. It starts beginning to sort of understand the world and trying to envision it. And the way it did that here is by creating some idea of a board and pieces and colors, etc. In my last video, I said it had like a visual representation, which is not really accurate because it's probably nothing visual as we understand it, but it is some understanding, some way that its neural net works that allows it for it to compute the full board state. Now, that paper didn't make too many waves, but just a few weeks later, out comes Harvard with this paper. And they say that these latent diffusion models, if you've seen those AI art things, that's kind of what that is. They have an impressive ability to produce realistic images, which is true. I'm going to add some images to this video that are going to be 100% AI generated, just to give you an idea where kind of we are right now with some of the latest technology. I use Midjourney, that's my favorite tool, but the other big one is DALL-E, and of course, as we'll see in a second, Stable Diffusion. That's another AI art/image generator. Those are some of the most well-known ones, but there's many others, of course. And so yet the inner workings of these models remain mysterious. And this is what a lot of people kind of talk about. This is the concern a lot of times. We don't fully understand what happens inside these neural nets. People describe it as a bit of a black box, right? We feed information from one side and then we train it, right? Which is this sort of back and forth process of adjusting all the various things in it. So there's like a forward pass, there's back propagation, it goes back and forth. And over time, slowly gets better and better at doing the output that we're trying to get, whether that's making a pretty picture or predicting the next word in a sentence or image recognition or optimizing ads or whatever. So we know the inputs, we know the outputs, but the inner workings are a little bit mysterious. We don't know exactly where and what it learns. Now, with these probes that we talked about, we get a glimpse into it. We can begin like detectives to kind of look at clues and analyze what's happening inside. So it's just slightly less mysterious. And so next they say, even when trained purely on images without explicit depth information. So recently they've been adding, as part of the training data, the depth information in images. But so even though in the past they've been trained without explicit depth information, they typically output coherent pictures of 3D scenes. And so when they did their research using linear probes, so this is similar to what they used in the Othello paper. I think they mentioned that Othello used nonlinear probes. Here it's linear probes. We find evidence that the internal activations of the system, we find evidence that they have representations of both 3D depth data. And they are able to distinguish between the background and the object, the main object of the image. And that these representations appear fairly early on in when it's trying to construct that image. If that's a little confusing, they have some pretty good diagrams that we're going to take a look at in just a second. And so they appear surprisingly early, well before a human can make sense of the noisy images. Noisy, think about distortion or static, right? If you have TVs with those old school antennas where it's like super distorted, you can kind of see a picture. Think of that as like a noisy image. Like there's data in there, but it's distorted, you can barely see it. And so these intervention experiments, these linear probes, they indicate that these representations play a very big role in image synthesis. It's a bit of a mystery how these networks transform, let's say, the phrase car in the street into a picture of a car in the street. Do they simply memorize superficial correlations between pixel values and words? And so in this work, we investigate whether a specific LDM, so that's these latent diffusion models, so think of them as the AI art models, they go beyond surface statistics, literally and figuratively. So again, here they're asking, can this thing create a 3D representation of the object it portrays in 2 dimensions? So that's a similar question that Othello asked. Like, we take this thing and we give it a billion 2D images. It has no idea about the existence of a 3D world. It knows nothing other than just these pictures, which are basically just a bunch of pixels that are sprinkled in a pattern that we might recognize as a 3D scene because we've seen the 3D world. We can be like, oh, I know that's a boat, and we know what would happen if you went and you looked down above it, or if you went and you looked from the side. We can kind of imagine that these things don't really have that experience. They don't have that data. They're just fed a bunch of images, a bunch of pixels in a 2D plane. So when we ask it, hey, can you do a 3D representation of it? If it's just spitting out the data that it learned, it would have no idea of what that means or how to do that. And so our probes find linear representations are both a continuous depth map and a salient object / background distinction. So salient object, just think of that as sort of like the object of the picture. So if there's a car in the street, the car is the salient object and the background is the street and everything on it. And also, as we mentioned earlier, so it seems like it's a pretty big part of how it generates these images. So, and this is part of sort of like this big debate that's going on. So our work fits into a long line of interpretability research. So basically, we're trying to figure out how to understand what these neural networks are doing. That's kind of a big part of this whole AI safety debate, right? Because people are scared, like these things are developing pretty impressive abilities and we have no idea what it's thinking, right? So if you ever see this sort of a green-looking monstrosity in memes or pictures somewhere, this is kind of like what often people that are concerned with AI safety, sort of how they choose to represent it. Eliezer Yudkowsky was probably the one that kind of started this, I'm not sure. And so how they're representing is like, this is the sort of the monstrosity, the AI that we have no idea what it's doing and how big it is and how powerful it is. But, we taught it to our LHF as reinforcement learning with human feedback, right? So we take this thing and it spits out some answers and we're like, good job. No, that's bad. And over time, it like figures out. So it puts on like the smiley face. It's like, oh, I know what they like. I'll put on a smiley face. And it says, I simply exhibit the behaviors that were engineered into my programming by my creators, right? But it's still this thing is just this little mask that it's wearing. And so to understand this sort of our ability to interpret what these things are doing is very valuable, not just for further figuring out how to build these models, how to improve them, but also, in our ability to interpret and to make them more safe for AI safety purposes. So the general question of whether generative neural networks can be characterized as merely aggregating surface statistics. So the people like Jan LeCun, the people that are arguing against this, they're like, it's just a fancy calculator. It's just a stochastic parrot. There's nothing that looks like learning or anything else like that going on. Right. And this is sort of an area of heated debate in natural language processing with some evidence suggesting that they do build world models. And the people that are kind of arguing for the fact that maybe they understand, they're not necessarily arguing against the fact that, yes, this is statistics. Maybe it is technically a stochastic parrot, but they're kind of saying, look, it seems like what's happening there is more similar to the human brain than we realized at first. So whatever name you want to call that, it does seem to be closer to human intelligence than we would have guessed, 5 years ago, 10 years ago, etc. All right, so this is kind of like how these images are generated. So as you can see here, it starts, you can barely see, you can barely tell this image. It looks like almost just random, like noise, like static, etc. And so over time, it gets to, okay, like that's a car. And so they're saying that these models have an internal representation of depth and saliency that develops in early denoising steps. And so this row 1, that's the decoded image. So this is kind of like how the model normally makes it. And so rows 2 and 3, so this is 2 and this is 3, are predictions of probing classifiers based on the model's internal activators. So as you can see here, it looks like the deep red is things that's in the foreground that's closer to the camera, right? And the blue is things that are farther away. And so like just looking at this first image, you probably can't tell that it's a car, but you know that there's some round thing that's closer to you. And then like the skies in the background or whatever that is farther away. And this depth from image, kind of shows the same thing. So you can kind of like, you can't guess what the object is, but you can kind of guess how far away it is compared to other points in the scene, etc. And the salient objects is sort of, that's like, what is the main object of this photo? Like here, it's a car, right? You take a child, you're like, what's in this picture? They're like, car, right? Like they're not going to say, oh, grass. Maybe some will, but most people will say, no, the car is like the main object, right? And so as you can see here, like step one, it knows that that's the main object, right? It begins early on to start forming it. And so the point here is that we told it to make images of cars and humans and this and that, right? And then we didn't really understand how it did that. It kind of figured out that a car sort of looks like this and a boat sort of looks like that. But then when we're looking at it, how it's approaching solving this problem, it starts with going, okay, wait a minute. What's in the foreground? What's in the background? How close is this to, my viewpoint, to the camera? None of those things were taught to it, right? It has no idea what the camera is or what a viewpoint is or what a background and a foreground is. It has no idea what these objects are. But somewhere along the line, it created this ability to compute what that is and figure out what that is. And that's actually where it starts the whole process. It figured out that, hey, like before I even begin to think about, the colors, for example, or even the edges, the precise edges, etc., let me just figure out what the sort of 3D space looks like, which is kind of crazy to think about it, because imagine trying to program that. Imagine trying to code that ability. It would be very difficult. But with these models, it just pops up. And so here they use Stable Diffusion because it's an open source text-to-image diffusion model used by millions of people. So Stable Diffusion, so I feel like it's like probably one of the biggest ones, probably in the top 3 or top 5. I mostly use Midjourney, but Stable Diffusion, I feel like that's the other big one. And it's open source, which is, I think, probably a big part of why they chose to use it. The other one is DALL-E, but that's by OpenAI. So they may or may not want to create papers around that. So choosing something that's open source is just a lot easier for them to see all the inner workings of it and probably less liability issues, etc. And so then you're talking about the probes, right? So probing classifiers take the intermediate activation of a neural network as input to infer some properties. So instead of like just running the whole thing from beginning to end, they stop it in the middle and then they open it up to see what the heck's happening inside. So probably similar how you can run a dishwasher, right? And you open it halfway through and you see, okay, what step is it? Is it splashing water, or is it just heating, or where is it in that process? By the way, I asked ChatGPT to make up a word that can be used to describe opening a dishwasher midstream, and said, certainly, how about the term disrupt? As in, opening the dishwasher while it's in the middle, it's a portmanteau of a dishwasher and interrupt. And I think it's also kind of like saying erupt a little bit, because if you open it and the water comes out, it's kind of like an erupt, disrupt, which, by the way, as far as I can tell, is not a word that's ever been used before. Like if we use Google Books Ngram Viewer, so this basically shows how certain words have been used before. So like if I put in like artificial intelligence, right, it probably got used very briefly here. And then right around 1994, it started taking off, then dropped to a low in 2007, and then skyrocketed again, fairly recently. But disrupt, ChatGPT might have invented a word, which is pretty insane to think about. And then they also briefly talk about how to uncover if there's a causal link. And so basically what they do is they modify the internal activations and measure the effects of the outputs, which is something that they talked about in the Othello GPT paper, which again, kind of to me, that's the thing about like poking the brain in one spot and then like your finger moves or whatever. They also do different experiments where they're able to like, I'm not sure if I'm using the right words here, but maybe shut down certain areas of the brain using some sort of an electrical current. Yeah, so I guess they were able to like turn off certain parts of the brain to see how that affects people. So you shut off certain parts of the brain and they're not able to like self-control themselves as good. There's areas of the brain that seem to be maybe they reduce belief in God, or some of them I know shut down certain ethical things. So this seems something similar, like, right, if we go in and we change something within that neural network and then we keep asking it to reproduce the outputs it did before, like what's the difference? Does that thing seem to correlate? Does that change seem to correlate to the output over here? So Stable Diffusion often creates scenes that appear to have a consistent 3D depth dimension with regions arranged from closest to farthest relative to a viewpoint. Also, they have images with bokeh effects. So these are the bokeh effects, where some objects are in clear focus and their background surroundings are blurred. And so they explored the world representation of depth from two different perspectives. One is a discrete binary depth, where each pixel belongs to certain visually attractive objects, or it's part of their background. And two, a continuous depth representation from the perspective of 3D geometry, where all pixels have a relative distance to a single viewpoint. So if you're looking at something, each on a 2D plane, you can think of each pixel on there as representing an object that a certain distance away from you, the sort of the viewpoint. And so the first one, where we think of each pixel as belonging to either an object or somewhere in its background, so that as the salient object detection task. So back here, that's this right here. So in this image, we know that the main object is here and all the other pixels is going to be around it. That's part of the background. And then that the probing for continuous depth dimension can be characterized by a monocular depth estimation task. We might look into that later. I'm not sure what that is. So here they're saying that they've synthesized a bunch of images so they can train this new model. And then they kind of estimated the depth so that they can have for these new images. And then this is basically saying that they took out some naughty images because, right, because they're saying like it's not that we're cherry picking, there's just some bad images in there that we had to throw out that were explicit or whatever. So here there's a number of pages where they kind of go deep into the math and understanding exactly how they went about conducting this experiment. So I encourage, if you have the time and interest, to read through this. But basically they created a bunch of images that were like humans, vehicles, furniture, animals, etc., that were objects. And so they found, and this is what we mentioned earlier, so that the depth dimension develops at a stage when the decoder image still appears extremely noisy to a human. So high probing performance at the early steps suggests that this is like kind of an interesting thing that's early on and figured out, okay, this is important. The depth of the image is important. And here again, so they're looking at basically kind of how the images are generated from early to late. So by probing, they basically stop at each step of the process and try to break it down. What is it thinking about it to produce the final image? So as you can see here, like the bike, appears here like very early on when we're talking about it, figuring out what the foreground is, what the salient object is, what is the main object, right? It's kind of like, it's a bike. And you can see that right there at the very first step. Whereas, if you're trying to gauge it based on the, how it decodes the image right here, like you're not going to be able to guess that it's a bike until like the very end over here, right? So I think this is the thing that guesses what the image is. It can't guess until the last two steps. But if you're looking at what it's beginning to think of as the main object, you can kind of tell it's a bike, like almost I would say at the first image, right? Definitely by the third, you're like, okay, that really looks like a bike. And same thing here with kind of like the 3D space, what's closer to you, what's farther away. Like right here, that the floor, whatever near the bottom of it is closer to you. Whereas the deep blue, those are the farthest things that you can see in the image. And yeah, exactly. Those are the windows that are showing the horizon, the beach and the horizon in the sky. So right here, you can't possibly predict what's in this, what these images are, but you know exactly what the 3D sort of viewpoint is. Anyways, a lot of this paper kind of goes deep down these rabbit holes that you really have to have a background in machine learning and a lot of the math. I'll link it down below, so if you're interested in learning more, I highly recommend it. But let's see what the conclusion was. Our experiment provided evidence that the stable diffusion model, although trained solely on 2D images, contain an internal linear representation related to scene geometry. Meaning we only showed it 2D images, it figured out some way of sort of simulating the 3D world. Started to figure out where the faraway horizon is, where things are closer in the foreground, etc. And that these representations emerge very early on. And they also have a causal link between those internal representations and the final image produced by a model. So these results add nuance to the ongoing debates about whether generative models can learn more than just surface statistics. But I'm curious to know what you think. Is it beginning to look like we figured out how to make rocks think? That we can dig up various metals and stuff from the ground, fold them into certain shapes we call a computer, and then somehow run the electricity through it that somehow simulates or mimics what the human brain evolved to do over however many millions of years? Or do you think it's just business as usual and this isn't anything new? If you do, I do want to know more. Like, what is it? What do you think about something like this? Now, after looking at this, it does seem like, and in the previous paper, Othello GPT, it's beginning to seem like these AI models, these neural nets, are coming out with these mental models about how to reason or think or whatever word you want to use. I don't think we have really good words to describe what it's doing, but it's beginning to seem like it does have something that we can call a mental model or some way of thinking about how to solve these problems that we never taught it, that we never explained it. We didn't even give it the data that it would need to sort of understand it, right? We give it 2D images and figures out how to build 3D scenes from them. We give it a bunch of moves from a game and figures out, oh, there must be a board and kind of like has a representation of that, what that board is. Another paper that recently came out that kind of caught my attention was when they're applying AI and these technologies to learning about the stock market. I mean, that's kind of an obvious application, right? This thing is you feed it tons of data and it begins predicting what happens next. For the global capital markets seem like the perfect thing to unleash it on, right? We have tons of data. The whole thing is just basically data that's like publicly available about companies and stock prices and trading volumes, and just everything is recorded with, you got to pay attention to details. You got to make sure it's correct. You know, if it's not correct, you might go to jail, right? If you're an accountant for one of these big firms, you better make sure it's correct. But my question is, if we take an advanced model like this and we feed it all the data of the stock market, is it going to develop some mental model of how stocks work that maybe is even more advanced than we're able to understand right now? That's one of the next subjects that I want to look at, is how are these being applied to stock trading? If you enjoyed this discussion and you want to stay tuned to the latest AI news, AI progress, explained simply and hopefully in a way that everybody can understand, please hit subscribe. This is what we're going to be doing on this channel for the foreseeable future. That and how to actually build some of this stuff, how to build AI agents and how to build AI applications, even if you don't really have a machine learning or a software development background. So hit subscribe. And if you made it this far, thank you for watching. My name is Wes Roth, and I'll see you next time.